This video is a recording of gathering data for analyzing the percent copper in brass through spectrophotometry. Here I'm dissolving some brass. You can see that I have 0.8956 grams of a brass sample. I'm adding some strong nitric acid to the brass. And brass is made of copper and zinc. So this means that both of those ions will be released as this brass dissolves. As we zoom in here, you may already begin to see bubbles forming. That's hydrogen gas that's released from the reaction of the nitric acid with zinc. Another thing that you might see starting to happen is a little bit of a bluish-green tint to the water. That indicates the presence of copper ions in solution. And this isn't so visible, but you might also see a brownish gas that's forming above the solution. That's nitrogen monoxide. That's a product of the copper reacting with the nitric acid. And as time goes on, the gas becomes more visible, the bubbles become more pronounced, and the greenish blue tint to the water starts to become really visible. This is happening inside of a fume hood because the brown gas that's coming off the top of there is toxic, and the acid is pretty strong acid that will dissolve lots of things. This actually happens pretty quickly, relatively speaking, but it's going to take about 10 minutes, so we're going to speed up the video in a sec and we'll watch this happen at high speed. Now as this is going on, you can see the brass is moving around as it's being dissolved. Water's getting a lot bluer. Less and less brass. And now there's no solid brass left. Everything has been dissolved. So the next step is we want to kind of analyze what color should we measure at. This is copper nitrate. You can see that it's absorbing at about 820 nanometers. That's what kind of a bluish color. This is copper sulfate. It absorbs in about that same range, so probably the copper ions are what's responsible for that, because that's common to these two solutions. Move these out of the way, make room for another compound. This is a solution of iron 3 nitrate. This has nitrate in it. You cannot see large absorbance at 800 nanometers, so the nitrate is not responsible for that absorbance. Here's another iron compound, kind of a similar brownish color. This is iron sulfate, and absorbs kind of in that reddish end of the spectrum, or bluish end of the spectrum. This is zinc nitrate. There's a little bit of a bump in the infrared, but otherwise it doesn't really absorb much of anything, which you'd expect because it's a colorless solution. So in the colorless zone, in the colored zone, there's not much absorbance. And this is zinc sulfate. Again, there's a little bump in the far infrared, so maybe that's where zinc absorbs, but it doesn't absorb very much. So when you put that information together, the iron compounds are probably, their primary absorbing color is not useful because there's no iron in brass. If you have to choose between the bluish color and the colorless zinc solution, obviously the bluish copper colored solution is what you want to analyze for. So about 820-ish nanometers is probably the right way to go, because that's where copper ions seem to absorb, and that's what's going to be the primary color producing ion. So we're going to use copper nitrate as a kind of a calibrator, a way to get our Beer's law curve. So this is 0.4 molar copper nitrate, and we're going to produce 4 different solutions by diluting this solution in 25 milliliter volumetric flasks. So I'm going to use a volumetric pipette, it's a precise tool for delivering a set amount of any solution. It's kind of like a fancy calibrated eyedropper. I draw some solution in there. I've got a squeeze bulb at the top that allows me to control this. And then I'm going to drain some of my 0.4 molar copper nitrate solution into the flask. Not very much of it. This sample is going to get 0.625 milliliters of my 0.4 molar solution. So I'm writing that down just to keep a record, and we'll look at all of these measurements when I get done. So now I'm going to grab sample number 2, and it's the same story, so I'm going to speed this up. I'm just giving a different amount of the concentrated solution into each one of these volumetric flasks, and we'll look at the actual amounts later on because I'm writing them down on the board. So there I have some 0.4 molar copper nitrate solution in each one of my flasks. The flasks are the same volume, and so the final volume of these diluted solutions will all be 25.00 milliliters. Now as we look closely, we can see the volume of the 0.4 molar solution that's been added to each one of the flasks. So use that data to figure out what is the concentration in each of these flasks once it's been diluted to 25 milliliters of volume. Now we're going to go through the dilution process. I just taken some deionized water. I'm going to add it to the flask to make it a full 25 milliliters of volume. So I'm getting close to the calibrated mark. So I'm going to switch to an eyedropper now and use this thin pipette to add water very carefully so that I can fill it right up to the mark. And I know then I have exactly 25, or precisely 25.00 milliliters of solution. It's kind of hard to see the mark there, but I've tried to fill it as close as I can so that the meniscus is right on the mark. Put a cap on it, and I'm going to invert it several times to make sure that the concentrated solution that came from my stock solution bottle gets mixed with the water to make a homogeneous mixture throughout the whole flask so that it's all the same concentration. So that was sample 1, 0.0625 or 0.625. And now I'm going to speed up the process because all I'm doing is diluting all these things, so you don't need to watch that slowly. And now I've got 4 solutions, each with a different concentration, all 25 milliliters final volume. The next thing to do is create my Beer's law absorbance versus concentration curve. And I'm going to do that with the use of this spectrophotometer tool that's connected to this laptop there. So the first thing I have to do is calibrate the spectrophotometer by putting a blank cuvette in here. So I'm just putting distilled water in there as my blank. And I insert this into the spectrophotometer. And it takes its calibration reading. Next, I'm taking the first solution. This is the one that's 0.65 milliliters of 400 or 4 molar diluted to 25 milliliters. 0.4 molar diluted to 25 milliliters. And I'm just going to put enough in the cuvette that it will catch the light inside the spectrophotometer. So I'm wiping off droplets from the outside. Place it in the spectrophotometer and tell the computer to take a sample. And then I'll have to enter the concentration that I calculated, which you should have done for each of those samples. So now I'm going to pull my cuvette and empty it out. Grab the second sample bottle. And I'm going to rinse it out with a small amount of solution number 2. And I'm going to do that twice just to make sure that there's no more dilute solution in there from the first sample that will change the concentration of my sample number 2. So now after these 2 rinses, I'm ready to fill this up with solution from sample 2. Got some bubbles in there, so I'm snapping the side of the cuvette to get them out. Wipe the droplets off the outside so that they don't distort the light as it passes through. And then I'll take another reading. So I'm going to do that for the remaining 2 samples. You've already seen how it's done, so we're going to speed through this. Sample 3, take a reading. Sample 4, rinse out the cuvette, fill it up. And now we're going to take our final reading for the 4th sample. So this is what we found. It's a pretty good correlation. You can see the slope there. That's going to be useful as we go to find out the concentration of our sample solution, our actual dissolved brass solution, so we can figure out the copper content later on. So now I have my sample of dissolved brass, and I'm going to dilute it. I'm going to make it a little bit less concentrated by taking the dissolved brass solution, that's the nitric acid with the brass dissolved in it, and I'm going to dilute it with distilled water so that its final volume ends up being 100 milliliters. So keep that in mind as you go to figure out the ultimate concentration and then ultimately how much copper by mass is dissolved in this solution. Speed through filling this up because it's pretty slow. Halfway through I stop and I'm going to swirl it around a little bit just to mix it. Make sure that I'm getting a nice homogeneous solution. I'm going to fill it up into the neck, close to the calibration mark at the top. Then I'm going to switch to a thin stem pipette again. And fill it as precisely as I can right up to the mark, which means I would have 100.00 milliliters of solution that I've created by this diluting process. And I'm going to invert it a bunch of times to make sure that it's mixed well. And now the last thing to do is to take the absorbance of a sample of the solution that has my brass dissolved in it. So remember, the volume is 100 milliliters. I'm taking enough to fill the cuvette to catch the light as it goes through the spectrophotometer. Like always, I'm going to make sure that I don't have any bubbles inside or any droplets outside that would change the path of the light. And I take my reading. And so I have an absorbance curve. If you zoom in, this is what it looks like. You can see that the major absorbance is right around 820, and the size or the value of the absorbance is 1.243. That's the absorbance. Now, putting that together with what you know is the slope of that calibration line, you should be able to work backwards to figure out what is the concentration of copper ions in that 100 milliliter sample. And from there, you should be able to figure out how much mass of copper was in the solution.